Hello, welcome back to another video about the introduction to atomic force microscopy, part 2. In this part, I would like to cover most of the topics of atomic force microscopy, always as an introductory level. We do not go into detail. There is too much to say, so it's just a bird's eye of this technique, which has the overall goal to describe, to measure actually the sample topography of a given sample at atomic resolution level. So we have seen that it's composed, the main element is this cantilever, which is a beam with features a tip, and there is our sample. Okay, so the idea is that whenever we reach the sample, there will be some forces that arises, which we are going to describe shortly, and the cantilever is also moved, let's say, into our direction. We can be, let's say, if we want to be tridimensional, into let's say x and y direction. So in order to map point by point, pixel by pixel, and gather information of the sample topography, which I would like you to think about not as a flat surface, but is composed by, of course, by atoms. So it'll be something that has some troughs, some peaks, etc. And the cantilever, which is, even the cantilever tip is composed by atom, will be feeling the presence of this atom as well as soon as it's moving into the x or y direction. Okay, but what is the origin of these forces? We introduced it a little bit last time. Let's make a scale just to give you roughly an idea of the order. If we want to make this scale in the nanometer, let's start from 0 to 1, 10, 100, and 1000 nanometer. Okay, we can identify different regimes according to the distance that we call z, but we will be more precise in a second, between the cantilever and the surface of the sample. And this first regime from 0 to 1, which we call a contact, okay, there are strong repulsive forces in these cases, and the origin of such repulsive forces are essentially Bohr forces and Hertz, let's say, allow me to call it Hertzian forces. Okay, in a second range, which goes from 1 nanometer up to 50 nanometers or so, is what we call intermediate contact. In this region, the origin of the forces are van der Waals forces, in particular is Keesum, Debye, and London, van der Waals forces. And in the last range, which goes from 50, approximately from 50 nanometer beyond, we have non-contact, in which the origin of the forces are magnetic or capillary in nature. Okay, so let's start describing The first one, okay, the contact mode. We said that in contact, the origin of the force is pore forces, which is true. The meaning is that according to the Pauli exclusion principle, no two electrons can have simultaneously the same four quantum numbers. So this will cause actually a repulsive forces, due to these electrons of the sample and of the electron of the tip put in contact. And so these are quantum mechanical reason for these Bohr forces to arise. And there are strongly repulsive forces. In a second, we will also see a tentative potential which describes this complex tip and sample interaction, because what we are doing here is tip, and I would like you to remind that this is the tip and this is the cantilever. And cantilever plus tip obeys some equation that we described in the previous video. So the tip sample interaction is what we are speaking now. Interaction. Okay. So we describe the Bohr forces. What is the Earth forces? What's the Earth? That's related to the Earth problem. Okay. In which if we have a hard sphere, let's say the blue one is a hard sphere that is penetrating inside a surface of a certain depth, which we call high, and which we call h. There are some forces that are repulsive forces, and allow me to put a little h down here to remind us that are Earth forces, which are proportional to this indentation to the power of 3/2. Okay, so because of this indentation, there will be experience a repulsive forces, which is proportional to the indentation itself. Let's move now on the intermediate contact forces, which are van der Waals forces. We said it's key sum d by London, but to be more precise, the key sum is van der Waals forces that are related to the dipole interaction. Okay, so our dipole, interacts with the other dipoles. Okay, and this is the region of the key sum. But this is not the only effect. As we know, the dipole may also causes in a neutral atom an induced dipole, and therefore this gives rises to the bi forces, which is related to the dipole induced dipole interaction. And lastly, the London one, which is related to the induced dipole interaction. Okay, then in the last we have non-contact forces, which is just electromagnetic forces or capillary forces. Okay, so all these complicated tip sample interaction are tried to be explained in terms of one single potential, which some of you may be aware of, which is called Lennard-Jones potential. So it's Lennard-Jones potential, which is a function of the z, where of course z is the distance between our cantilever and the sample. Also, this is z, okay? And this potential is as a particular shape. It's let me write it and then comment. It's C1 over R to the 12 minus C1 divided by R to the 6, where this part here, this part here is the repulsive forces, whereas this other part is the attractive forces. Because when the tip is approaching the sample, okay, so let me picture it this way. When the tip is approaching the sample, there will be some attractive forces which is causing the cantilever to bend toward the sample. So the cantilever is actually bending toward the sample, okay, this way. And if we bend too much, if we approach too much, they will be in contact, okay, so we will have cantilever that start to get in contact this way. And if we still pushing the cantilever down, what we will have is that is still bending, but is bending in the opposite direction, okay. And the reason for this change of the curvature of the bending direction, there is an inflection of the cantilever, is due to these repulsive forces. So it's somehow complicated, and it's getting worse, as I will tell you in a second. But if we want to depict this behavior with the Lennard-Jones potential that I wrote here, okay, we can see something that is like this. Okay, so this is the shape of the Lennard-Jones potential. If we are far away from the sample, so Z is very high, so we are in this region, to say, we see that the effective potential in this case is very low, almost zero, so there are no forces. But as soon as we get closer, okay, to the sample, so we are doing this exercise that I show in a second. So we started from here, we get closer and closer, okay. We will reach a certain point in which there is a change of the trend, and the forces become repulsive, like in this case, okay. And so in this case, it's coming repulsive all the way. So if we decrease Z below this Z naught, to say, the forces become repulsive. And the Lennard-Jones potential grasp this fact. If R is very little, okay, we will see that this part here will go to zero much more quicker than the other part, because it's elevated to the power 12, the other one is elevated to the power 6. So if R is bigger a certain value, that's going to zero, and the predominant effect is the blue one, is the attractive forces. On the contrary, if the distance is closer to is getting closer to zero, the predominant contribution will becoming the one in yellow or in green. So they're repulsive forces, okay? So we can also maybe see it in a different way, because there is more, as I promise you. The fact that this is a potential allows us to think about in terms of forces as minus the gradient of such potential. Okay, so if we want to plot instead of the potential the directly the forces, we can do it. We just need to plot, try not to make a mess. We just need to plot the forces as a function of the distance, okay? And I need to make some correction, because whenever we have a maximum here, or to be precise, a minimum, we have a change in the derivative, so I will need to shift this this way. Okay, something like that. Of course, there will be some changing in the overall shape of the curve, but essentially this is the changing point of the contact to non-contact, where the forces become repulsive. So we also see that from this point onward the forces are positive, so are repulsive. I don't know how to, from this point onward is repulsive, and from this point downward is attractive. Okay, but it's actually, there is more than that, and the more can be seen again using this plot, which highlights some features of this kind of techniques. Okay, let me clear a little bit more this plot. Okay, and again, it's force as a function of the distance. One aspect is that imagine that we are approaching our sample with a cantilever. So this is always sketching the sample, even if it's not flat, remember that. And the cantilever that is going down, okay, from a position going down. We can think this in this plot as going into, from this point maybe, into here, okay? But if the cantilever is getting closer, is deflecting toward the sample, as we said, but it's kind of like in a static, in an equilibrium condition, because the attractive forces that are caused by the sample tip interaction is counterbalanced by the spring coefficient of the cantilever itself. So it's kind of an equilibrium as we approach it. The more it's going down, the more it's bending, but at the same time there is this equilibrium. But there is a moment, there is a particular distance in which what's happening is that the gradient, okay, when the gradient of the forces of these attractive forces exceed the gradient of the elastic forces, so the gradient of the force attractive become bigger than the gradient of the elastic forces, which appears to be, since is remember is k, let's say z, it appears to be exactly the spring coefficient. So if the gradient of the attractive forces exceed the spring coefficient of the cantilever, if this condition is met, what we have is, and imagine that is in this dot here, A, what is happening is that the equilibrium is lost, and the tip is all of a sudden jumping on into the sample, okay, and is jumping from A to A prime. So it's not following that curve, it's jumping from A to A prime, and this happens because the equilibrium is lost when the gradient exceeds the spring coefficient of the cantilever. Of course, we can change the spring coefficient of the cantilever by changing the shape, by changing the type of cantilever itself. There are different ways of making it, but at the end of the day, when this gradient exceeds the spring coefficient, it will jump to contact. So this is called jump to contact. Okay, and now if we are going farther, okay, it's keep increasing until the force has become repulsive. Okay, and let's say that we stop here and we start to go back. We want to go back, we go back, we go back. We start going far away from the sample, and we reach again the A prime point. So one would expect that there is a jump off contact, right, in this position, and is going back to A prime. But this is not so. This is not what is really happening. What's experimentally is happening is that it proceeds farther. Let's say the point here, I make this part to compress. So the point is that it's going a little bit farther, and from this point it goes back, let's say from B to B prime. Okay? And this cycle continuously occurs, but the origin of this part here are the capillary forces that are holding down the cantilever, the tip of the cantilever as is trying to goes out from the sample. So there is some imagine like this is the sample and this is the tip. There are these capillary forces which are somehow holding down the tip as it tries to goes up. Okay, they are holding down, and that's the origin of this A prime B displacement into the force distance curve. And this is called jump off contact, of course. Jump off contact. So, okay, we have seen that the tip sample interaction is somehow complicated. It's not simple. It involves different type of forces and different aspects that one at the first grasp might not be considering, but they are there, and they are all important for the overall understanding of the working principle of this technique. Okay, but how do we actually know this Z? Because I said that we are moving from the cantilever itself. Okay, we have our sample down here. We can think this distance, we can think this distance as piezo distance Z. We have learned that the cantilever may bend, it bends, okay, like this, and we can call this delta cantilever. But what is also possible, what is also happening, is that the sample itself deforms because of the presence of the tip of the cantilever, and we also call this delta S as delta of the sample. So what is actually the distance? So the distance, okay, which may think as this distance here, effective distance, we can think about as Z minus the delta C plus delta S. So this is the effective distance between the tip, the bottom part of the tip, and the upper part of the sample. As it's deforming, the tip is bending, and so on and so forth. But how do we measure it? We said last video that there is a laser beam, okay, and the laser beam is pointing into the head of the cantilever and is reflecting. Let's make a different, let's do it this way. Is reflecting, and this goes into a detector which is maybe located at a distance d from the tip, and it's a position sensitive detector. So if we know that this the delta of the position sensitive detector, okay, this is equal to what? We need to imagine that there is some alpha angle, and 2d tangent of this alpha angle is effectively the distance measured by this delta PSD. But if the angle is smaller, we know that this is 2d alpha. And this alpha we actually calculated in the last video. We can recalculate it here. We need to consider that, remember, no, it's y, the curvature is proportional to the bending moment, which is f of z L minus y divided by ejz. So if we integrated, we have a rotation, we have our alpha that we are looking for, which is f of z divided by ejz. This is ly minus y squared over 2. We specify this in u equal to L, it's prime actually, so f of z ejz, and this becomes L squared minus L squared half, so it's L squared over 2, okay? But what is Fz? We know that delta z is, we introduced last time, c, it's c f of z, but c is L to the cube divided 3 ejz f of z. So we replaced, instead of f of z in there, we write delta z over c. Okay, so we use this one. So we have u prime L, which is our alpha, is equal to delta z over c, but c is L to the cube divided 3 ejz. L squared 2 ejz. So this one simplifies. It becoming, this one simplifies. So it's 3 delta z over L, okay? And this is alpha. So we go back to this equation. So the delta PSD is equal to twice the distance with the photodiode alpha, but alpha is 3 delta z over L. Okay, so from this, if we reshape it in this way, we have delta z is equal to L delta PSD I'm sorry, I forgot that there is a 2, which of course simplifies. So it's L delta PSD divided by 3D. Okay, so essentially delta PSD is L, we know. Okay, this is the length of the cantilever. The distance also is known between the cantilever and the detector. Therefore, by measuring this delta PSD, we are effectively capable of determining this delta Z, and we assume this is the delta of the cantilever, okay, in this picture above. So this quantity here effectively, okay, is what we can measure by measuring the delta of the PSD. And we can also identify some regimes. Okay, let me take this down. Okay, some regimes. Let's start with the first one. The first regime is if we assume that the sample is effectively undeformable, so delta S is equal to 0, and there are no surface forces, let's call it. There are no surface forces, okay, and the sample is undeformable. We can see some force distance curve. Particular first, we can think about making some plots. The intensity and the distance. Okay. In this regime, the first regime, what we have is that okay, is almost like this, is perfectly fact, so no current measured, E equal to 0 for different distance. At a certain point, there is a linear behavior of the intensity of the current with respect to the distance, okay? So this is the separation point of contact to non-contact under these assumptions of delta S equal to 0 and no surface forces. And we can see a similar example in the force distance curve, okay, where we have all of a sudden a changing of the forces in this way as we reach a certain distance. What else we can say about this? We can say that there is a parameter which is the delta E and the delta Z, or delta D, as we like. So delta E divided by delta Z, this is called the sensitivity. Okay. And if we want our delta C is the intensity measured at the PSD divided by the sensitivity, so it's divided by delta E divided by delta Z. And the forces as a function of the distance is effectively K delta C. Okay, so I think we can move to the second case. In the second case, we have again delta S is equal to 0, as to say. So the sample is still undeformable, but there are, yes, surface forces. So we switch on the surface, the surface forces, we switch it on. And what we have is, I don't know why it's not copying, it's doing whatever you want. Okay. And there is a different, of course, behavior in this case. As we switch on the forces, what is happening is that there is a transition, okay, from this regime into a linear regime here, and therefore there is like a transition curve like this that goes from a transition curve into a linear regime, which occurs to be at a certain point here. And also for the force distance curve, we have something like this. So as the distance decreases, the force tends to increases. At a certain point, it's going up as the forces, as the distance is constant, the forces increases. The third case is the case in which we suppress again the repulsive forces, no surface forces. Okay, these repulsive forces which were responsible for this behavior here, in here. But we say that the deformation of the sample is different from zero, which may be the cases of some organic material. And in this case, what we have is something like that. This it goes in this way here, okay. And also for the force distance curve, it's something that is going like this. And lastly, but not least, the case in which everything is switched on. So we have both delta S different from zero and yes surface forces. So in this case, we have the effect of the jump to contact, which were described earlier. So we have a behavior that is going like this. At a certain point, there is all of a sudden a drops in the intensity, and it goes up like this. And this is also captured in the force distance curve, okay, where we lose control. And then it goes up. So essentially, we have reached a position in which the gradient of the attractive forces exceed, as we said, the spring coefficient of the cantilever, and the tips is jumping into the sample itself. As it jumps, it penetrates inside. So whatever we can think about contact is somehow like a mess, okay? But this is what it is, and this is what we need to describe. And so, yeah, this is it. What is limiting this is, of course, some thermal fluctuation and some noises in our measurement, but definitely the atomic resolution can be achieved. What are the types of mode to run this atomic force microscopy? So the operational mode, can be of two types, can be static and dynamic. Well, it's not actually static, it's just to distinguish it from the dynamic. In the dynamic, we are deliberately making the tip vibrating, so the tip is vibrating deliberately closer to the resonance frequency for a reason that we will see in a second. To differentiate of this, we have the static case in which the cantilever is not vibrating at all, it's as we described so far, so it's letting it approach the sample, and as soon as we will measure some bending, let's say, let's sketch it. Okay, even in this case, we have a constant force mode or a constant distance mode. Essentially, the principle is that as it reaches a certain point, a certain pixel, we move of the tip to the next pixel, and of course the force regime will change, because unless the surface is flat, there will be or higher peak or lower peak, and this will causes a further deflection or inflection of the cantilever, and the piezo device will restore the original position, and this restoring is what is actually being used to map the sample topography according to this shifting up and down of the cantilever. Okay, so this is for the static. For the dynamic mode, we need to think the cantilever as let's say as a spring, mass spring system, which is forced and damped, of course, because there is the damping of the maybe it's simpler to write down the equation, so we can think about an equation of motion which would be something like this. We have our omega 0, let's say, is the natural frequency of the cantilever z, and there is some let's to say some driving forces, so this is the driver excitation, and an external forces of external. So this external force is actually due to the tip sample interaction, whereas this driven excitation is because the cantilever itself is connected to a vibrating driver, which is effectively moving, shaking up and down. So the cantilever is vibrating with a certain amplitude. Okay, and everything is described by this equation of motion of the damped harmonic oscillator, forced and essentially the important point is to focus the attention of this f of z, of these external forces, because if this force is sufficiently small, we can think about Taylor expanding it, and if we Taylor expanding it, say not z, I'm sorry, but this is n 0 to infinity is 1 over n factorial, the derivative of f of z times z minus z naught power n. So we need to Taylor expanding, and we have let's say f z0 plus we interrupt it to the first order, so this is f of z z minus z naught, which we can rewrite as the gradient of the forces times z prime. So we can rewrite the above equation here, making use of this what we have just introduced in terms of the gradient. So the modification that there is of the dynamical responses because of this gradient, and we can gather up all the terms that are equal. We highlight this gradient here, z prime we have f of z divided by m, and again we have the omega t. Okay, so this is the reshaped. Then we can call this quantity here omega prime, and we see that the effective change in the frequency of the resonant frequency is proportional, okay, is proportional by this gradient, okay. So if to summarize, we make this cantilever vibrating in dynamic mode. We make it vibrating with a certain frequency by means of this driver excitation, and because of the vibration and of the interaction forces, the effect of the interaction forces is to modify the dynamical response of the cantilever. In particular, it modifies the frequency. There is a shifting of the frequency which is proportional to the gradient of the attraction. And because of this fact, we can introduce the two modes, which is the dynamical mode, which are called AFM, which stands for amplitude modulation, AFM, sometimes called tapping, and AFM, which stands for frequency modulation, AFM, okay, or non-contact mode. Okay, if we start with the amplitude modulation, what we have is that we start far away from the sample, and we start far away in the sense that there are no interaction in the place where we start to make our experiment. We deliberately bring the cantilever closer to the resonant frequency, not exactly to the resonant frequency, but closer. And the reason, because it's closer, there is this gradient effect that we have just shown that is modifying the dynamic responses. So the gradient is somehow important. So we deliberately bring the cantilever closer to the resonance frequency. And we are actually reading the amplitude on the piezo of the photodiode. We are reading this vibration of the cantilever in the photodiode, and we set up an amplitude. We decide that there is a specific amplitude that we are deciding to use, and as we have set up this amplitude, because you need to imagine that if we are far away, the only part of the equation that is counting is this one, okay, with nothing of this part. And of this part, the left part, without the external forces, we know everything, so we can estimate the amplitude, which we can think about something that goes square root of omega prime minus omega squared minus 4 z omega, something like that. Something like that, which is the amplitude that we measure. And but as soon as we approach the sample, okay, there will be a modification of the amplitude, okay, and in part because of the gradient of the interaction, and the modification of the amplitude will cause an increasing or a decreasing of the amplitude according to the distance. we generally pick a decreasing of the amplitude because we want to stay into attractive regime of the forces, and the device actually stops when it reaches the amplitude that we set at the beginning of the experiment, okay? And from that point onward, let's say that the cantilever is arriving here, it's measured a certain amplitude. It stops where the amplitude is equal to the fixed amplitude that we decide, and then it's moving in the x or y direction to the next point, okay, where probably there is a changing in the amplitude because of the topography of the sample, and therefore there will be a shifting up or down due to the piezo in order to restore the same A star that we fixed at the beginning. So it's shifting up and down, let's say A prime, and then it moves to the next point, again a second, until it fixes the amplitude, and so on and so forth. And keeping track of this changing of the position of the piezo in order to maintain the same amplitude that we fixed at the beginning is what is actually used to measure the topography of the surface. In the frequency modulation, on the contrary, what is kept constant is the amplitude itself, and as the system is moving in the action, as the tip and the tip is moving x and y on the sample, there will be a modification of the frequency according to the gradient of the interaction forces, which will increase or decrease the frequency, but the driver will maintain the same amplitude constant. So what is actually measuring is we are directly measuring the changing of the frequency due to the gradient of the interaction, and therefore it's possible to keep information of the topography of the sample by measuring this directly, this delta frequency. So we should keep in mind that we might not have a precise understanding on where we are in a distance-like position, so we don't know where we are, but what we know is that the relative displacement that there are in terms of amplitude or frequency as we are mapping the sample. So this pretty much concludes our quick introduction to atomic force microscopy. There should be thousands of different things to discuss, but of course cannot be covered in just 2 videos. So thanks for watching, and probably the next video will be about scanning electron microscope, scanning electron microscopy. Thank you very much. Good night.